Welcome back to Operating Systems Crashcast. I'm Victor, and with me as always is the brilliant Sheila. Today, we're diving into a crucial aspect of process synchronization, hardware support. Sheila, why don't you kick us off with why we need hardware support for synchronization?
Absolutely, Victor. So, listeners, imagine you're trying to coordinate a group of friends to enter an escape room one at a time. You might think a simple software solution would suffice, but in reality, we need some hardware backup to make sure our synchronization efforts are truly effective.
That's a great analogy, Sheila. In the world of operating systems, we're dealing with multiple processes or threads that might be trying to access shared resources simultaneously. Software-only solutions can be vulnerable to timing issues and interruptions. That's where hardware support comes in to save the day.
Exactly, Victor. One of the fundamental concepts in hardware synchronization is the idea of memory barriers. Can you explain what those are?
Of course. Memory barriers, also known as memory fences, are hardware instructions that ensure the order of memory operations. Think of them as traffic lights for your computer's memory. They make sure that all memory operations before the barrier are completed before any operations after the barrier begin. This is crucial in multi-core systems, where each core might have its own cache.
That's a great explanation, Victor. Now, let's talk about some specific hardware instructions that support synchronization. One of the most basic is the test and set instruction. Can you break that down for our listeners?
Certainly. The test and set instruction is like a special lock on a door. It checks if the door is locked, test, and if it's not, it locks it, set. All of this happens in one atomic operation, meaning it can't be interrupted halfway through. In technical terms, it writes a 1 to a memory location and returns its previous value. This allows us to implement a simple lock mechanism.
Excellent analogy, Victor. Another important hardware instruction is compare and swap, or CAS. This one's a bit more complex but incredibly powerful. Imagine you're trying to swap out a light bulb, but only if it's the specific wattage you're expecting. That's essentially what CAS does with memory values.
Great explanation, Sheila. CAS takes 3 parameters, a memory location, an expected value, and a new value. It checks if the memory location contains the expected value, and if so, it replaces it with the new value. All of this happens atomically. This instruction forms the basis for many lock-free and wait-free algorithms in concurrent programming.
Absolutely, Victor. These hardware instructions are fundamental to implementing higher-level synchronization primitives like mutexes and semaphores. But there's another concept we should touch on: atomic variables. Can you explain what those are?
Certainly. Atomic variables are special variables that guarantee that any operation on them happens as a single, uninterruptible unit. It's like if you could instantly teleport a book from one shelf to another, without any chance of someone grabbing it midway. These variables rely on the hardware instructions we just discussed to ensure their operations are atomic.
That's a fantastic explanation, Victor. And it's worth noting that many modern programming languages provide atomic types as part of their standard libraries, abstracting away the complexity of directly using these hardware instructions.
Absolutely right, Sheila. Now, let's talk about why this hardware support is so critical. In a multi-core system, where you have multiple processors or cores executing instructions simultaneously, software-only solutions can fall apart due to race conditions and other synchronization issues.
Exactly, Victor. Without hardware support, we'd be trying to solve these problems with one hand tied behind our back. The hardware instructions we've discussed provide the foundation for building reliable, efficient concurrent systems.
Well said, Sheila. And it's not just about correctness. These hardware mechanisms also provide significant performance benefits. They allow for fine-grained synchronization and can often avoid the need for more heavy-handed approaches like locking entire data structures.
Absolutely, Victor. In fact, many modern processor architectures have additional instructions beyond what we've discussed today, all aimed at making concurrent programming more efficient and reliable.
That's right, Sheila. And as we move towards increasingly parallel systems, understanding these hardware primitives becomes even more crucial for operating system designers and developers.
Absolutely, Victor. Now let's do a quick recap for our listeners. We've covered the need for hardware support in synchronization, explained memory barriers, and discussed key hardware instructions like test and set and compare and swap. We also touched on atomic variables and their importance in concurrent programming.
Great summary, Sheila. I'd like to emphasize to our listeners that understanding these concepts is crucial for anyone working on operating systems or concurrent programming. In interviews or real-world scenarios, you'll often encounter questions about race conditions, deadlocks, and how to prevent them, and hardware synchronization primitives are a key part of the solution.
Absolutely, Victor. And remember, while these hardware mechanisms provide powerful tools, it's still up to the programmer to use them correctly. Understanding their capabilities and limitations is essential for writing efficient, bug-free concurrent code.
Well said, Sheila. And with that, we'll wrap up today's episode. Thanks for tuning in to Operating Systems Crashcast. Until next time, keep your processes synchronized and your hardware humming.
Goodbye, everyone, and happy coding.